Hello and welcome to the next part in the Pathfinding series. So this time we are going to be looking at building up our actual pathfinding system. So previously we got our path data set up. So that was our network of points and edges that connect those points so that we have that for the entire map. We set that up so it was built at different resolutions. And we also set up stuff so we knew what areas were connected so that we could very quickly and easily tell if two locations on the map connect to each other. So we've got all of that infrastructure set up and our focus is now on how to actually find those paths in it. So with pathfinding, there's a lot of different algorithms. There are many different algorithms. The best algorithm is really going to be down to the circumstances that you're operating under. Now, for this, the algorithm I'm going to show you is one of the stock standard ones that's very well understood. It's been around for a long time, known as A star. It is sort of a parent of many different types of algorithms. There's a lot of related ones to it, and it's a really well understood one, and it's a really good basis for being able to get familiar with how we set this stuff up. So let's dive in. So this is what we've already got to begin with. We have our path data, and we've got, if you remember, here's our set of edges, and we can see the areas where there's disconnects due to steepness of slope, things like that. So we've got everything we need to start doing our pathfinding. So what I'm going to do is, under our scripts, I'm going to create a dedicated script for our Pathfinding Manager. Now, the other thing we're going to need is, if we take a look at our, and actually I'll move that to its own separate folder. So we're going to have pathfinding. So we need, because we've got multiple sets of path data, one of the things we're going to need is we need to know which set of path data we're actually referring to. So that's something where, and we want to keep an eye on the size of our path data and things like that as well. So we'll set up a folder for all of this. So I like the idea of generally having a central manager that pathfinding goes through. The reason I recommend doing that is it just makes it so much easier for being able to manage and balance performance. If everything's going through that one point, it means you can set global settings very easily for how much work's able to be done in a particular frame, for example. So Pathfinding Manager, and make sure that's got the script linked up. Good. So our Path Data Manager, we've got these different data sets, but we don't have a way of uniquely identifying them. So that's something where we're going to need to be able to uniquely identify them. We also could just directly refer to the particular asset, but when we're doing a pathfind, we need some way of knowing, okay, what set of data am I working with? So what I'm going to do is, for our Path Data Manager, where we have our setup here for the path data set, I'm going to give this a name, or a unique ID. And that unique ID, I'm also going to bring that over to our actual path data. And we'll make that part of the initialization here, just so that that's all saved out. So we've got an easy way of being able to refer to the path data. So we've got a unique ID. Good, and then we just need to pass that through down over here. Path data set. And let's make sure we get that named properly. Always fix typos as early as possible, because the longer you leave it, the more of a hassle it is to fix. So we'll just give these simple IDs one by one. So we'll call this humanoid. one by one, and this we might call maybe for vehicles, 4 by 4. That works. And then we'll regenerate our path data, because that way then that information is stored for it, and we'll be able to see that that will be in our path data files. So just want to confirm that we do actually have that properly stored before we start doing the next bits. And we should see when we look at this, unique ID is in there, which is good. So, okay, Pathfinding Manager. If we start looking at setting this up, so this is going to be the central point that everything talks to. So if everything is talking to this, that's one of the things where this is going to need to be a singleton. At least it's going to be easiest. We don't want to be doing find components or find objects all the time. We want to just be able to quickly, easily retrieve the particular object. So public static pathfinding manager instance get and a private set. And we'll default that to null, and our usual pattern in awake where we set instance is equal to this, but before that we check instance is not equal to null. We'll return and we'll destroy whatever game object we are attached to and just log out an error. So found duplicate pathfinding manager on, and then we'll just output the game object name, just as an extra little bit of safety there. Okay, so we need to be able to request a path. So if we think about for requesting a path, that's going to mean we need to give it a start and an end location. So let's start off with this being public void, and we'll go for request path. And then, okay, start point. So it's going to have start pos. It's going to have a end pos. So that's an essential thing. We need to know what path network we're talking to. So I'm going to put that at the beginning. So path data unique ID. So, okay, start pos and end pos, path data, unique ID, that seems reasonable. We need to get that path back as well. So what that path actually looks like, well, it's probably going to be a set of our path data nodes. So I would say what this would return is that. So we could say that this returns a list of a path data node. And that might be null if it's failed. So a bunch of different things we could be returning there, but there actually could be circumstances beyond just, okay, a path doesn't exist. Could be that the path is too long, so we might find we need to differentiate that. That's okay. What we'll do is we're going to build up a basic version of this, and then we're going to look at some of the issues, some of the ways that we can improve this. So that's one of the things. A-star is very well studied, which means there's a lot that's been written about it. And that means it can be hard to find good information about it, and in particular, hard to find stuff where we are being able to make it perform really well. And the tricks you need to make it perform well actually can vary from language to language, because how we allocate memory is something that is very fundamental to the performance of A-star. So fundamentally, the way A-star works is we have our starting node, which is our start point. We then look at the neighbors around it. We'll then pick one of those neighbors to explore. Then we look at the neighbors around it, and we keep doing this process till we reach the end. Now, how it picks which node to explore is based on costs. So A-star calculates 2 costs for every node. The first thing it calculates is the cost in terms of how much did it cost to reach that node. So to get from node A to node F, how far did I have to walk? What was the cost for that? Then it makes an estimate of the cost from that node to the destination. So when it's picking which nodes to look at, it picks ones based upon which has the lowest total cost. So which one we think is likely to be the best resulting path out of that combination of how much did it cost us to get there, how much will it cost, do we think it will cost to get to the end. And cost, well, cost is typically distance. It doesn't have to be. This could be something like fuel or time. And what we use as our cost is what we are optimizing. So we say A star finds the shortest path, typically. What would be more correct is to say A star finds the lowest cost path. Cost is often distance, but if you want something to find not the shortest distance path, but the fastest path, you would use cost as being your time. If you wanted to find the most fuel efficient path, then you would use fuel or energy as your cost. So what you use as your cost is what the pathfinding is going to optimize, what it's going to have as being the shortest value. So that's an important thing. We will use distance in this case, but we could very easily use other ones. And that will give very different behaviors. You know, the path that something will take shortest distance versus if you're saying fastest time will be quite different typically. So that's an important thing. It's minimizing costs there. So that means one of the things A star has to maintain is so A star when it evaluates, what we'd call processes a node, it never processes that node again. So we need to maintain a list of here are the nodes that we have processed, what's called a closed list. We need to maintain a list of the nodes that are to be processed or potentially to be processed. So our candidates, these are the ones that we find we look at our neighbors, those become candidates. We then look at, we grab another node, we find its neighbors. Those are further candidates. That's called the open list. At the end of a pathfind, the open list will typically still have things in it. If the open list gets empty, that's a failure condition. That actually means we can't find a path. We've run out of nodes to evaluate. So closed list keeps track of the ones we have visited. Open list keeps track of the ones that we potentially need to visit. So we're working with things that are dynamically changing in size. If we just use the default things of a list for all of those without anything extra, our performance is not going to be great because there's a lot of memory allocations there. So we need to minimize those. The other thing that you'll often see in descriptions for pathfinding is in the actual path data nodes, storing the costs. So there's the G and H costs they're referred to. I cannot emphasize enough how much I recommend against doing that. Do not store that extra data in the path data. The reason for that is it starts to get really messy in terms of it's a lot of memory overhead, because if you want to have more than one AI path find simultaneously, your path data now balloons out in size because you're storing two costs and a link to a parent for every node. So that means if you did no optimizations, you're looking at 12 bytes per node. Our path data for 1 meter by 1 meter has 1 million nodes, so it's 12 megabytes. We could probably get that a bit more efficient. We could probably, with some careful trickery, get that down to maybe 4 to 6 bytes. That's still 4 to 6 meg per AI that we want to pathfind simultaneously. Even back 5-10 years ago, 16 AIs pathfinding simultaneously was common in first-person games. In sort of your strategy games, you would have dozens, hundreds of AIs pathfinding. That's not tenable. You would have huge memory overhead. So we need to find ways of being able to avoid that. So we're not going to store stuff in path data. What we are going to do is we are going to set up a class, and this is going to be storing our temporary data for the pathfinding. So this is going to be our pathfinding request or our pathfinding data. So the key thing with this is part of the reason why I'm setting up stuff in this is also we don't want to necessarily have to always complete our pathfind in one go. We might want to do a little bit of work and then the next frame do a bit more and then a bit more. So spread the performance hit. So we want to encapsulate it nicely in a single package. It's going to make it a lot easier for working with. So again, the typical thing you would often see here is what you might go for is, oh, okay, well, we'd have a class and, like a pathfinding node, and that would have a link to the pathdata node. That would have our costs, everything like of that. And then in here, we would have a list or an array of our pathfinding nodes. And in C#, that is going to be atrocious for performance. The reason being is because this is a class, every time we add one in, there's a memory allocation. So it's a lot of memory allocations that we'd be doing at that point. So that approach of having a list of those classes is typically known as an array of structures, an AOS approach. We are going to be going for an SOA, a structure of arrays approach. So rather than having a list of those nodes, we're going to have multiple arrays here. So we're going to have stuff like, okay, our G costs, and this will be an array. We're going to have our H costs. So G costs are the costs to reach the point. H costs are our estimates, what's called a heuristic of the cost to reach the end. We're going to have an array of our parent IDs. So, okay, we'll have this. We also want to keep track of whether we have visited a node, so a node status. So I'm going to set up here, I might put it in here for now. So system.flags and enum node status, and we'll have none. We'll also then have visited. So open and closed is what we'll use for this. So open means it's in the open list. Closed means it's in the closed list. So we're keeping it very simple with the setup for this. And again, the status of these will all just be another array, because these arrays, we can allocate full set of them in one go, and it's going to be far quicker from that allocation point of view. So statuses. So that looks pretty good. We've got the key bits that we're needing there. We will adjust and update this as we go, but that gives us the key initial sort of stuff that we need there for this. Okay, so let's look at what we need to do for requesting a path. So first thing is we're going to need to retrieve the path data set that this is corresponding to. So we're going to need to be able to say, hey, Path Data Manager. Now it doesn't currently isn't set up for being a singleton, but that's okay. We're going to be able to go get path data UID. And we want to check that. So if path data is equal to null, then we'll fail out at that point. So return null. Again, make it clear that something's gone wrong. Could not retrieve path data. Let me just log that out. So we're going to need to make our path data manager a singleton as well, and that's okay. We've got most of what we need for that. So we'll just rig that up. And then we need this helper function for get path data. So we're going to set this up, public path data, get path data, string unique ID. So then we just loop through our sets of path data set in path data sets. If the unique ID matches, then we'll just return that data. Otherwise, we return null. So that's all we need for it. So, okay, we've retrieved the path data. So first step is we need to find the node for our start and end position. So var start node is equal to, so that's something where our path data, so we've already got get node stuff, and we've got get node ones that take a grid position, but not ones that take a general world position. So we're going to do this, and again, we'll check if start node is equal to null, then we fail out. So debug log error, and then we'll just be able to say failed to retrieve node at, and we can just output the position. So start pos, and we'll return null. So retrieve the start node. And we'll do the same thing for the end node. So these are all little bits of setup stuff that we must do to begin with. So this is our end pos. End node. So that's good. Now we check the area IDs. Check the area IDs. So if start node area ID is not equal to end node dot area ID, we know there's no connection. So we return null. No path exists. We also can check, so it's that, or if our start node, because remember our area IDs start at 1, so if it's less than 1, it's not valid. Or if end node area ID is less than 1, it's not valid. So we do all these initial checks to ensure that when we start a pathfind, that we have a reasonable expectation of being able to have it complete. We want to very early on be able to identify and reject a case where there is no valid path data, no valid path. So now then this comes path data node get node vector 3 world pos. Now this is an interesting one because this one we want to ensure we could do this by doing a search. We really don't want to do a search. We want to be able to track down locations very, very rapidly. Now, conveniently, we have this cell size, and we already know that we've got these calculations here that should be working for retrieving the cell. So what we should be able to do is say we take worldpos.x, and I'm going to actually bring this maths down here, and we'll actually work through from first principles, just reversing this maths. Because what we've got is this is worldpos.x is equal to this part. We don't need the y. And then this is worldpos.z is equal to this. So we want to be able to refactor this because, so x, if we remember our x value here, that's with our grid position, that is our column. So this is actually column, and this is row. So we want to reverse this so that row is on the left-hand side here. So that means if we divide this And I'll actually swap these around a little bit so it's a little bit easier for us working with. So I've got this. And this is something I'd recommend if you're struggling with working out the stuff. Write it out and work out the maths from first principles. So, okay, if we divide this side by cell size.x, then we've got this reduced to this. So we've already simplified it. We do the same thing here. Divide that. So, okay, we've got these much simpler. And then what I would do is, not strictly necessary, but I would bracket these. And then we minus 0.5f, 0.5f. So now we've got row and column is equal to that. Now we want these as an integer. So we want an int row and an int column so that we can then just do a return get node row column. So we need to integerize this. So what I'm going to go for, because I suspect is going to be the correct thing, this is something where we will be doing testing to make sure. We do a floor to int. So mathf floor to int, like that. Might be a case that we need to slightly adjust either of these. That's okay. So what I will do then is debug log start node world pos, and I'll debug log start pos because we would expect those to be fairly close to each other. So this is something where I recommend testing each of these little bits along the way as you go. Really, really valuable. I'm going to set up a public transform start marker, public transform end marker, and then just do a request path. And we'll be able to set here public string path data UID. This will just make it easy for us testing it. So start marker dot position, end marker dot position. It's just going to make it nice and easy for being able to test that this is working. So in terms of which path data we're going to be using, we're going to start with the humanoid. And then what I'm also going to do is I'm going to create a couple of things. I'm going to put a capsule here. That will be our start marker. And then we'll also have an end marker. I'm intentionally just going to have these pretty close to each other at the moment. And we'll link those up. And what we're wanting to see is, in particular for that start marker, how closely that location sort of lines up. It's something we want to see. So let's run this. And so we can see start pos and then the node. That looks pretty close. So we've got a difference of 0.4 in X and 0.1 in Z, which is good. That looks like it's within a cell because they're 1 meter cells. So that looks pretty solid. I'm very happy with that. I am going to move this out of update because that's probably a little too spammy. But the key thing is we've got our nodes. And what I would be able to do is, so we will only get that if those points are actually connected. And if you remember up here, we're not going to have path data because those points are going to be fairly separated. So if I put that up here and then run it, what we're hoping to see is that it's going to tell us no path exists, which is good. So we've solved a couple of the key initial things. We have our locations, we have the corresponding nodes. We're ready to start pathfinding. So I'm going to set up our pathfinding data. So we want to go pathfinding data, and this is going to be our context is a new pathfinding data. I might actually rename that to pathfinding context. I think it's going to be a better name for it. So this, I want to be able to initialize all those arrays. As I said, I want to have as little memory allocation as possible. And in particular, well, as fewer memory allocations as possible. So I want to give this the number of potential nodes I might have. So path data, nodes, length. And so we'll set up here, so public class pathfinding context, and I want to be able to say num nodes, and then I'm going to initialize all of these things. So statuses, oops, not class, is a new enode status, num nodes, and we do this just with all of our particular ones here. So G costs, H costs, and our parent IDs. We'll get those initialized. Now, some of these, we are going to need to set them to have initial values. So we're going to go through for int index is 0. And so intentionally with a lot of this stuff, I am not using for each loops because they do have a bit of a higher overhead and there is a lot of data we're traversing. So you'll see a lot of using of traditional for loops here. So index is less than num nodes plus index. So in terms of initial values, well, parent IDs, I need a way of indicating that there is no parent set for something. So I'm going to go with -1. Costs, I'm actually going to initialize those to the maximum possible value for a float. That may change what we end up using that for, but I think that will be a good sort of one to initialize to. Initialize our data. Statuses will start at 0, which will mean the nodes are unflagged, which is good. So that looks good so far. I'm going to set up our open list. Now, this is something where a general list is actually not going to be the best for performance, but I want to be able to illustrate the difference we see in performance. So open list, and that's going to be a new list of path data nodes. So it looks good. Got our context. So set up our pathfinding context, set up the context. So the first thing we do is we need to add our starting node to the open list. So to do that, well, we need to work out our costs. We also need the helper functions for this. So it's going to be add, so open node, start node. Now, in terms of costs, so, well, G cost is easy, 0, because we're standing at the start. H cost, we need a way to estimate cost for this. So I am going to set up so that this, we have to pass in a function that can evaluate that cost. So I'm going to go for having system action, and we give it 2 path data nodes. Calculate cost. And then what that function will look like for now is going to be a delegate current. Actually, might call that origin rather than actually a current, and then next or destined or Naming of these things is always tricky. Target, destination, I think is better. So this is going to have a delegate that will calculate the cost, and I'm going to keep that delegate really simple. And I'm just going to have it return the vector3 distance, current world pos, and the destination world pos. So to have this be able to return the value, we actually, rather than using system.action, we use system.func. So action doesn't allow returning values there, but with func, the last parameter is the return value. So this way we can pass in a custom calculate cost function. So we can say calculate cost, and we can go start node, end node, and that will give us back our cost. And then the final thing we're going to need to set is the parent, and the start node has no parent there. So open the start node. So I'm intentionally doing most of the logic for this inside the pathfinding context. So this will have a public void open node. So what we have is our node. Then we have our G cost. Then we have our H cost. And finally, we have our parent. Int parent ID. So, okay, well, adding to the open list is easy. We just go open list, add node. But we need to store our costs. So that means we need to know the index that we're storing these things at. So our path data node, if we go and take a look at them, so they already have a grid position. And we already have stuff where we are working out a unique index for them using this approach of row by column. So already have stuff where we're doing that. So we could actually put a dedicated function on our nodes here that give us back that unique ID. So public int unique ID. If we take a look, we're using column, so our grid pos x, plus our grid pos y, but we actually don't have all the information we need. So this is one where unique ID, we'll actually keep it there as a variable. We won't save it, so this is not data that's getting saved, and it doesn't need to, because what we're able to do is when we actually load our nodes here, we can just store it. So nodes, node index, dot unique ID is equal to node index. So we just actually store it out. We don't need to do anything extra in terms of that regard. And then when we're loading, we do a similar thing here. So we've got the index, and that just gets stored directly in there as it was before. So, okay, we can get our index. That means what we're able to do is very quickly set up things like, okay, well, statuses, node, and its unique ID is equal to enode status open. We can then very quickly set all of these other bits. So that's our G cost. We can then set our H costs. And finally, the parent IDs. Okay, so that's good. Nice, quick, easy way for being able to open a node. So we've got the node open. So then our core loop in A star, how that looks is while context has open nodes, or let's put it as open list, not empty, then this is where our core logic hits. If we hit this point, This is actually a failure condition. So debug log error, no path could be found. We've exhausted the open list. So our core check is that we've got stuff in the open list. We'll set up a little helper property. So that corresponds to open list count is greater than 0. So that's good. So what we're doing here is loop while we have nodes to explore. So the first thing we do in A* is we retrieve the lowest cost node from that open list. So our context is going to need to give us that. So we're going to need to be able to go context, hey, give us the best node. So that's going to give us a pathdata node, best node. Now that will always succeed. So we know that it will succeed. What we want to check first is, well, okay, best node, are you our destination node? That's the first thing we want to check. If best node is equal to end node. Because if it is, we're done. We've found our path. For now, I'm just going to return null, but I will log out here. Path found. So we've reached the destination. So if that's the case, we exit. If we haven't, then what we do is, firstly, that node, we put it onto the closed list. So move to closed, best node. So as soon as something is removed off the open list and we've evaluated it, then we move it to the closed list. Move to the closed list. So I'm going to set these two functions up now. Now move to closed is pretty straightforward. So public void, move to closed, pathdata node. And this is the really trivial part with this. We're able to just say, okay, well, open list, remove node. And we can say statuses, node, unique ID is equal to closed. Now that remove, I will probably put that into the get best node function. So pathdata node, get best node. So this has to find the lowest cost node. So pathdata, and what I'll do is I'll keep track of the index. So for doing this, there's a few different ways we could do this. The often easiest way is I'm actually just going to search through. So int index is equal to 0, index is less than open list count index. So I want to get the total cost for each of those nodes. And so that total cost, that G plus H, is something we refer to as the F cost. So I want to be able to keep track of the best F cost, which I'll start at float max value. So again, I'm going to set up here a public float get F cost, and we give that a pathdata node. That's just going to be return G costs. So G costs node.uniqueID plus H costs node.uniqueID. So we're doing just array lookups really quick, which is great. So node cost is going to be get F cost open list index. F node cost is better than our current best F cost. Then we'll track that. So best node is equal to null. And best node. So if the cost is lower, then we say best F cost is equal to node. And we can also then say best node is equal to that node that we're currently looking at. Now, there is additional stuff that we could do here to resolve tie breaks, and that's something where on a regular grid, tie breaks are a lot more common because it's regular, so the spacing between things can be very similar. So that can mean that we get two ones that have identical F costs, but different G and H costs. So it is something where you can set up a little bit of a tiebreaker in those scenarios that can give you a little bit of an improvement. It's not a huge amount, but it can give you a bit of an improvement in terms of being able to find the efficient path or find the path more efficiently. They'll always give you back the same path. It's just that one might give you that quicker. So, okay, that's good. We've grabbed the best node. We have checked if it's the destination. We've moved it to the closed list. Now we need to find its neighbors, and we need to process each of its neighbors. So our nodes have already got a grid location. We also already know for the nodes which potential neighbors they actually have. Because if we remember on the nodes, we set up these neighbor flags that we can check. So what we're going to do is, again, to make this stuff that we can do in a loop, I'm going to set up a thing here where we're going to have our const eneighbor flags, neighbors to check, and then that is just going to be our new eneighbor flags. And we can provide the particular values. So this is where we can just give it each of these flags. And I'm just pasting the stuff in because it makes it a little bit cleaner and quicker to get these up and running. So we have our particular ones, and we just need to prepend for all of these, the enum, so that it knows what we're talking about. And then we just clean up some of the extra bits here. So that looks good. We don't actually need that to be constant because that's the thing we're just going to be referring to in a couple of key places. Okay, we've got our neighbors to check. We also, just as an easy way of being able to, remember we had our offsets. So I'm just going to bundle these up as well into just a pair of arrays that we can loop over. So these are our neighbor offsets. Here's a new vector3 int, and then we just paste that in. It just makes it a little bit quicker. It saves us having to, we could do like, and you'll often see a get function that's going to loop through and do a bunch of extra calculations and put stuff into lists and everything like that. We don't want to do that. We are going for making this as fast as we possibly can and as few memory allocations as we possibly can. So stuff like this where we can manually set up our arrays is going to be making things a lot easier for us. And then we just mark all of these as being in grid helpers. Now, this is something where a regular grid allows us to do this. This is part of the reason for going for a regular grid. If we didn't have a regular grid, that's where I would be looking at storing that edge information inside the path data itself so that we can very quickly look things up. Usually outside of the nodes tends to work a little bit better for performance, but essentially being able to really rapidly iterate over those neighbors really can help out a lot. So what we can do here then is for int neighbor index is equal to 0. Neighbor index is less than our neighbor to check length. We add to that. Then what we do is we need to check firstly if the node has that actual neighbor. So we'd be saying, okay, well, best node dot neighbor flags ANDed with neighbors to check neighbor index if that has that particular flag. So we actually already have a built-in has flag. So we can check if it's got that particular one. If it doesn't, we skip it. No neighbor exists. If it does have it, then we can retrieve it. So we would be saying path data node neighbor is equal to our path data get node. Well, we know our best node's grid position, and we can add to that our neighbor offsets at this current index. So that's good. We've found a neighbor. We need to check if that neighbor, so in terms of what we do with that then, if that neighbor is already in the closed list, that means it's already been one that we've pulled out of the set here, which means we do nothing with it. So first thing we do is we ask the context if that's closed. So f context is node closed neighbor. And if it is, we do nothing. So ignore f closed. So we'll set this up here. Public bool is node closed, path data node, and we can just go and check our statuses. Node unique ID, that is equal to closed. And while we're here, because I know we're going to need it, I'm going to set up a similar one for checking if a node is open. So this is one of the advantages of these array setups. You have to do helper functions, but it then makes a really clean, nice interface down here. So then we check, is the node open? So f context is node open. Now I'm not going to fill that out initially because there's a couple of key things we need to do with that. But if it's not open, we open it. So we know we can go context and open node. We give it the neighbor. We know we need to give it the gcost, so we'll get to that in the moment. So I'll just put gcost there for now. Hcost, well, that's easy enough. We calculate the cost from the neighbor to the end node. And the parent, well, the parent is best node's unique ID. Now for our gcost, that builds up. So that's the cost it's taken us to reach this point. So that means the gcost is equal to the best node's gcost. Oops, we need to go context get, and we don't have this function yet, but we'll set it up. So get gcost for the best node, plus we calculate the cost from the best node to the neighbor. So it's getting the cost that it's taken to reach the best node, and then that cost for going from it to that neighbor. So we've got that total cost there. So we'll set up our get gcost function. So it's a bunch of extra little functions we set up here, but it does make for a really clean interface down here. So, okay, we've opened the node. Now we've got this case of if the node's already opened. And this is a really important thing, and this is one of the things that allows algorithms like A* to give us really good efficiencies, is it can find new shortcuts. So if the node is already open, we want to check if we've found a better path. So we want to work out this gcost, so the cost to reach this neighbor from the current node. And then we want to check, because the node's already open, so we'll already have a gcost. We want to check if we found a better gcost. So if this one is better. So if that gcost is less than context get gcost for the neighbor. So have we found a shorter path? That's what we're working out there. And here we're working out the cost to reach the neighbor. It's the same thing we're doing down here. So, okay, we've found a shorter path. That means we need to update this node. So context, we update open node. So we're updating neighbor. We're saying, well, here's a new G-cost. We've found a better path. And here's the new parent. So it lets us find shortcuts. So have we found a shorter path? So we're going to have this update for open node. And we'll put that here. Public void, update open node. So again, we have our path data node and G-cost. And we have the new parent ID. So we don't need to update stuff like the H-cost because the H-cost won't have changed because the H-cost is based on where that neighbor is located, so nothing changes. So all we need to update is our G-cost and our parent ID. So this should mean it's, in theory, able to find a path. We've got the key bits that we need in there. Let's test and see, is it managing to find the path? So I'm going to make sure I've saved the scene. This is stuff that you can very easily end up in infinite loops, but it said path found. Cool. Let's improve this a little bit. I want to know how long it took to find the path. So I'm going to set up int num iterations. It's often a thing that we check. And I'll set up a interface here for this, which that num iterations. I'll make that public, gettable, but not publicly settable. Iteration complete. Num iterations. We'll just add to that. So I just want to know how fast it found it. So in, and we'll log that out, num iterations. And what we do is every time we retrieve a node here, we go context, iteration complete. Could actually probably put that into get best node. So every time we pull one out, that actually might be where I put that in instead. I think is a better location for that. It's useful to track this just because this will spot any potential things. If you're seeing a huge number of iterations, that's usually a sign something is wrong potentially with your heuristics. A* is very efficient. It's generally not going to need a lot of iterations. So we'll run this. So 128 iterations. If we look at the distance between these, so 429 is about 10 meters in X, and it's about 20 in Z. So that's not too bad actually for number of iterations. That feels about right. So that's good. We've got a path. Let's stress this a little bit because these are really close together. So I'm going to take our start and I'm going to move it quite a distance away. And let's see performance-wise now. So it's still pretty darn fast. And that's down to how we have structured this. So by structuring it with using that structure of arrays approach, it makes it significantly faster. So I'm going to test it now with this. This is quite a long distance. This should be a very large number of iterations. And it was, but it was fast. And that's the key thing, is we want this to be really fast. But let's actually get our path coming out of this so that we can see that, because we want to be able to debug our path and be able to view it. That's going to be really important. So the way we reconstruct our path at the end here is pretty straightforward. So we know we've reached the end here. So I'm going to set up a list path data nodes, path, or found path is a new list of path data node like that. And then what I do is while best node is not equal to null, found path, insert at 0. So insert lets us place it at a particular location. So insert at 0, best node. Then we want to retrieve its parent. So if best node, we get the parent ID for that. So context, get parent ID. For best node. So this is where we would store this parent ID. And then we would retrieve the node based on that. So best node is going to be path data, get node. And this is going to be another get node function where we can just give a index, an ID for it. So I'm going to put that into there. So that will insert it into all the things, and we return found path, which what we'll do is we'll then draw that path that we found. So we need get parent ID as a function up here. And we can add that in with these. So public int get parent ID node. So we actually walk backwards. We start from the end and we walk all the way back to the beginning. So we return parent IDs, node, unique ID. That will give us that. And then we just need another helper function to give us the necessary data. And so that's trying to convert to a type that it doesn't recognize yet, because we need to say public path data node get node int unique ID, and then do some safety checks first. If unique ID is less than 0 or unique ID is greater than or equal to node's length, then we return null. So we just do a little bit of safety checking there. Then we need to decompose our index into the particular values, which we can see here how we do that. So we decompose this, and this is the X value there is giving us our column. This is giving us our row. So go unique ID. Then we can just do return get node row column. So that looks good. So we'll have our path, and what we'll do is we're just going to set up to draw that path. So var path is equal to, and for each var path node in path. And then what we do is we say debug, draw line, path node, world position to path node, world position +5 times vector 3 up. That should mean we get our path nicely being drawn. And we might need to set a time delay on that so that we can see it properly. So we'll put that there. So yes, we will just change this so that it will display it for, let's go for quite a lengthy time period. We'll say we do color. Let's make it really stand out, and let's make it for 10 minutes. We won't normally do that, but just as a temporary thing, that will make it easy for us being able to look at and see the path. And so we can see that's looking pretty good. It's following along the curves and reaches our destination. So we have functioning pathfinding. Now, we've got this running pretty efficiently. We can set what path networks we're wanting that path from, and that would be a good thing for us to check and make sure, okay, we did test it with humanoid 1 by 1. Does it work reliably with the vehicle one? Remember, it was about 30,000 iterations for the humanoid. This should be significantly less, and it is. So it found a path, and much less in the way of iterations. You can see, going from 1 by 1 to 4 by 4, it's gone from being 30,000 iterations to 1,200. So about a little bit under a 30th of the cost there. So huge difference in terms of performance and cost. But we've got functioning pathfinding running pretty efficiently. Now there is one thing I want to do, a final couple of little bits, because I want to see exactly what the performance of this is like. And so what I'm going to do is we're going to do a little bit of stuff for measuring the time that things are taking. So for measuring the time that this takes, I'm going to use the stopwatch system. So we have system diagnostics stopwatch, and I'm going to call this pathfinding. So that's going to be a new one of these stopwatches. So what we do is we go pathfinding start. Actually, I might call that pathfinding timer. And then as soon as it's done, we do pathfinding timer stop. Then we can log out the pathfinding timer.elapsed. And we actually have a few different ones there for that. We can see the elapsed time in milliseconds, things like that. So actually, let's go for elapsed milliseconds. And we're going to see how long this takes. So we've got a fairly lengthy path for this, and we'll run it a couple of times. So we're seeing 610 milliseconds. Let's run it again. Similar again. So we're probably going to see fairly similar times there. So that's good. So we're now at a great spot. We've got path data working reliably and quickly. We've got pathfinding working reliably and quickly. Now, what we're going to be looking at then next time is with the pathfinding, taking it a few steps further. So we're going to look at stuff like being able to have asynchronous pathfinding. So pathfinds that we can queue off and then can come back and update later, being able to balance a little bit the performance. And we'll also look at a few other sort of safety features that we can add in there with the pathfinding as well. Now, if you're looking for the code for this project, the code for it, the link is in the description below. It's available on GitHub. You can use that code in any of your own projects, whether those are commercial or non-commercial, you're freely available to use it. If you've got questions, chuck in a comment below. If you found the video helpful, please do chuck in a like and subscribe. It is something that really does help out and is very much appreciated. If you're looking for other ways to support the channel, I do have a Patreon, and the link to that's in the description below.